Section 9.1, Composite Functions. Functions frequently occur in which some quantity depends on a variable that, in turn, depends on another variable. For instance, a firm's profits may be a function of the number of items the firm produces, which may in turn be a function of the number of employees hired. In this case, the firm's profits may be considered a composite function. In general, the composition of f and g is written f circle g, or the composition of f of g, or f composed with g, and is equivalent or defined as the following: the f of g of x, where we'll use our order of operations working from the inside out to simplify this. Let's take a look at an example. We're given p of x is equal to the following rule, and r of x is equal to 2 of x plus 5, and they're asking us to find p circle r of x. This notation is sometimes intimidating simply because we're not used to it, but if we use the translation, the first function goes on the outside of the inner function, and then it's a matter of using substitution to get us started. R of x, by definition, is given here as the rule or expression 2x plus 5. And now we're evaluating the function p of this term, and wherever that variable is, we will replace it with this binomial. So the function p says take 3 times the x, and our x now is a binomial, square it, minus 4 times that value, which is 2x plus 5. We're done, other than the exception of simplifying this further to simplify our final answer for the function given here. In this next example, we have the composition r of p of x, which can be translated into the r of p of x. Working from the innermost, let me slide this back down so we can see our rules. P of x, by definition, is 3x squared minus 4x, so substituting p of x for the expression, we now have the function r of this quantity. R says take whatever is in the parenthesis, times it by 2, and add 5 to it. So we will take 2 times the value, 3x squared minus 4x, plus 5, and simplify this as well for our final answer. We'd use our distributive property and add 5 for our final answer. Up here we would have squared the binomial, multiplied it by 3, distributive here, and combined any like terms as seen. In this last problem here, they're asking us to take the composition p of r of 2. So notation-wise, by definition, an equivalent would be the function p of r of 2. And working from the inside, we want to find what r of 2 is so that we can substitute that in. Well, r of x is defined as 2x plus 5. We want to know the specifics of what this is equal to when x is 2, so we'll replace x with a 2. So we end up with a 2 times 2 plus 5. Multiplying first, we get a 4 plus 5, which ends up giving us a 9. So since r of 2 has a value of 9, we can simplify our composition function by putting a 9 in place of the function. And now all we need to do is evaluate the function p when x is equal to 9. you can't see p of x any longer, but this was the definition for p of x, and it simply means wherever x is, we are going to place a 9. So we have 3 times 9 squared minus 4 times 9. Squaring first, we get an 81. We'll do our multiplication. 3 times 81, 1 times 3, 3 times 8 will give us a 243 minus 36. 13 take away 6 is 7. We borrowed 1 from our 4. 3 minus 3 is 0, leaving us with 207. To turn this around and to help us with some understanding of composition of functions, we have the following variation. We're asked to find f and g of x such that h of x is equal to the composition of these two functions. So what we need to do is replace h of x with f composition g of x. That's always a cumbersome notation, so instead we'll do the f of g of x. And then look at the rule. If you think of order of operations, what's on the inside first thing that you would do is the quantity in the parentheses. That's what we're going to replace our g of x with. So we have f of g of x, which is 5 minus x squared, here in the parenthesis. And then that quantity is being squared, so g of x just got replaced with this. And furthermore, it needs to be raised to the third power, so our function f of x must be taking whatever the variable is and cubing it. So to simplify, or to identify what is here, g of x we are setting equal to the quantity inside the parenthesis, and f of x is taking whatever that is and raising it to the third power to do the final operation of h of x. So we list it as a generic x to the third power. To check this, you then take the composition f of g to verify that this in fact is the correct solution. In this next problem, same strategy. We're trying to determine what composition f of g of x is equivalent to this result, and we do have some options here that we can use for simplifying this. And keep in mind also that there is no unique solution. There is I won't say infinite, but there are multiple possibilities for what exactly f and g of x are. Again, going back to order of operations is helpful to determine what's being done here. Before we could take 7, which would be the last thing we want to do, which in this case would be the f of function, we would have to simplify our denominator. So to help us simplify this, we are going to have the denominator act as our g of x. G of x, being the denominator, would be plugged in first, and then to handle the f generically would be to take 7 divided by generically some x term. So to simplify or to represent what we have here, g of x is equal to 4x plus 2, the denominator. That replaces the denominator. F of x then is saying whatever you have, take 7 divided by whatever you have. So I believe this would be a version. And just to show you a check on this, what is the f of g of x? In place of g of x, we will put the value 4x plus 2, substituting it in. The f function says, whatever your variable is, put it in the denominator with 7 as the numerator, so this will go in the denominator, and we have our h of x that was given, which verifies we have successfully identified an f and g of x for this problem.